Welcome back to machine learning. This video will cover learning theory. In this video, we're trying to address several questions that you may have now that you know how to build many different learning algorithms. Is learning always possible? How many training examples will I need to do a good job learning? And is my test performance going to be much worse than my training performance? A key notion throughout is that simple functions and simple models generalize well. Theory serves two roles in machine learning. Theory after, which is to justify and help understand why common practice works, and theory before, suggesting new algorithms and approaches that turn out to work well in practice. Often, it turns out to be a combination of the two. In providing theory after, we make improvements to the existing algorithm. Theory can also help you understand what's possible and what is not possible. By understanding what is not possible, you can focus your energy on things that are. One of the biggest practical success stories for theoretical machine learning is boosting. Remember AdaBoost? William of Occam was an English friar and philosopher. He's most famous for what later became known as Occam's razor. The principle behind Occam's razor basically states that you should only assume as much as you need for a given problem. In machine learning, we paraphrase this as simple solutions generalize well. In other words, if you have 1,000 features in a problem and you can explain your data with just 5 of them, then you should use only 5 instead of 1,000. Some important terminology includes the word hypothesis. Instead of thinking about algorithms and models as a single classifier, we can think about it as a set of hypotheses that can be generated. A decision tree using binary features has a finite set of hypotheses, or trees, that can be built. It may be large, but it's finite. However, for a linear classifier, the set of hypotheses is infinite. You can draw an infinite number of lines, no matter how many features there are. Sample complexity is the number of examples required for your algorithm to achieve its goals. Occam's bound states that suppose A is an algorithm that learns a function f from some finite hypothesis class h. Suppose the learned function always gets 0 error on the training data. Then the sample complexity of f is at most log of the size of h. In a no-noise setting, a decision tree will always fit the training data perfectly. The only remaining difficulty is to compute the size of the hypothesis class of a decision tree learner. For simplicity's sake, suppose that our decision tree algorithm always learns complete trees. That is, every branch from root to leaf has length d. So the number of split points in the tree, that is, places where a feature is queried, where we ask a question, it's 2 to the d minus 1. Each split point needs to be assigned a feature. There are d many choices here. So this gives us d times 2 to the d minus 1 trees. The last thing is that there's 2d leaves of the tree, 2 to the d leaves of the tree, each of which can have 2 possible values, depending on whether this leaf is classified as a +1 or a -1. So that is 2 times 2 to the d, which equals 2 to the d plus 1 possibilities. Putting this all together gives us a total number of trees that's d times 4 to the d. Applying Occam's bound, we can see that log of d times 4 to the d examples is enough to learn a complete decision tree. Occam's bound is a fantastic result for learning over finite hypothesis spaces. Unfortunately, it is completely useless when the hypothesis space is infinite. If you want to establish sample complexity results for infinite hypothesis spaces, you need some new way of measuring their size and their complexity. A prototypical way of doing this is to measure the complexity of a hypothesis class as the number of different things it can do. Even though there are infinitely many hypotheses, there are only finite many behaviors. So if we're talking about binary classification, there are a finite number of ways that points can be classified. If we're talking about a linear classifier, We just said that there's an infinite number of linear classifiers, but there's only a finite number of ways that we can classify the data we've been given. With this insight in mind, the VC dimension was introduced. That is the Vapnik-Chernovenkis dimension. It's the maximum number of points for which you can always find a classifier from H that perfectly classifies the data. The terminology usually associated with this is the number of points that can be shattered by a particular classifier. We'll come back to that terminology in a minute. Formally, the VC dimension states that for data drawn from some space S, the VC dimension of a hypothesis space H over S is the maximal K such that there exists a set X in S of size K, such that for all binary labelings of X, there exists a function F in the hypothesis space that matches this labeling. In English, it means that the VC dimension of a set of classifiers is the maximum number of points that can be perfectly classified no matter what the labeling of the data is. In general, it's much easier to show that the VC dimension is at least some value. It's much harder to show that it is at most some value. In order to show that it's at least something, we just have to show that we can shatter one set of points. In order to show that it is at most some value, we have to show that it cannot shatter any set of points. Let's use an example to clarify. If we have the 2 points in this graph, we can label them any way we want. We can say both points are -1, only the red point is -1, only the blue point is -1, or both points are +1. Let's assume we're using a linear classifier. Could we get 100% accuracy on this data in all 4 configurations? The answer is yes. Instead of thinking about the configurations, you can think about drawing lines that shatter the data into these possible subsets. Let's do it. If we want both of the data points to have a -1 label, we can shatter it like this. This is a linear classifier, and the green arrow is just pointing in the direction of the positive class. So it's representing basically our W. Now, if we want the blue circle to be positive and the red X to be negative, we can use this linear classifier. If we want X to be positive and the circle to be negative, we can use this linear classifier. And if we want both of them to be positive, we can use this linear classifier. What does this mean? It means that the VC dimension of linear classifiers is at least 2. Let's try 3. So to classify them all as negative, we can use this line. To just do one as positive and the other 2 as negative, we can use this one, and this one. And then to do pairs of points, we can use this line, and this line. And then to get all 3 points as positive, we can use this line. What does this mean? It means that the VC dimension of linear classifiers is at least 3. Now let's try to do it with 4 points. With 4 points, we start putting lines in and we can get each point separated from all the other ones. And then we can get some pairs, but then we run into problems when we're talking about pairs on the diagonal. There's no way to separate the red X and the purple circle from all the other points without some kind of nonlinearity. This does not show that the VC dimension of linear classifiers is only 3. It does show that for this set of points, I can't use a linear classifier, so I haven't shown that it's at least 4. It turns out that linear classifiers have a VC dimension of exactly 3, but we have not shown it by choosing one set of points. We'd have to go through and show that no matter the set of points, there's no way to shatter it. The VC dimension tells us what kind of problems our model can solve. Learning theory plays a serious role in machine learning. A lot of work is being done as learning theory after, but it's an important step and it's good to know what you can and cannot do. In this video, we touched on a very small portion of learning theory. We talked about some terminology, We discussed Occam's bound and the VC dimension. The next topic for this class will be machine learning and society.